Hello, students. We are getting into chapter 7. It is our last chapter. We will be getting through decimals, operations on decimals, the idea of repeating decimals, which are super cool. And then we'll hit percents and real numbers. And again, real numbers are kind of there. We may end up rolling some of that over into Math 106, but we'll have to see how that goes. Let's take a look. So the big piece to start with is that we just came out of fractions, right? We just got done doing fractions. I'll click on the next page. And the idea is that fractions are kind of the fundamental idea of a part of a number. Now, if you kind of remember our place values to this point in time, let me come over here and kind of remind you, we had place values of ones, tens, hundreds, thousands, right? Those were our place values for base 10. And every time, if you kind of look at it, what we're doing is we're taking the ones, let's say, and we multiply by 10, and that gives you groups of 10. So here's ones, tens, multiply by 10 again, multiply by 10 again. So we have a beautiful geometric sequence. And if we were to just go the other direction, then we would be dividing by 10. And if we kept dividing by 10, we would need new numbers. So again, 1 divided by 10 would look like this. So we'd be counting by objects that are fractions of a whole number, which would be the 1. So the first one, as you can kind of see, is fractions with a 10 in the denominator. So we call those tenths. Then if we do that again, divide by 10, as we saw in class, dividing by 10 just means you put the 10 in the denominator as well. We'd be at 1 over 100. And lastly, 1 over 1,000. So that's where we get tenths, hundredths, and thousandths. So just be aware, there's a big difference between the tens place and the tenths place. Okay, so tenths you need to think of as like dimes, right? They're a fraction a part of a dollar. Tens would be like $10 bills. Okay, so very, very different. How many dimes does it take to make a $10 bill, right? Now we're starting to see some place value ideas. Phew. Okay, now does it keep going? Yes, it keeps going. And all the place values that you had going to the left, they mirror going to the right. But just be really careful with this. If you want to kind of understand, the ones is kind of our central location. After that, everything is either multiples of 1 or fractions of 1. So the line between whole numbers and fractional pieces is right there in the ones place. So what we've done, and you can kind of see up here at the top, if you take a look, in the United States, we tend to write things with a decimal point. In Belgium and France, they use a comma. So 6,75 would be the same thing as 6 plus 75 hundredths. That's in Belgium and France. Here in the United States, we would write this number as 6.75. Okay, and again, you notice how I read that. 75 of this object, and this object is 2 place values. Come back up. 2 place values takes you into the hundredths. Okay. All right. So naming the numbers is going to be important, as you can probably imagine. And let's start off with the idea of terminating decimals. Now, the reason why we start with terminating decimals is these are the ones that are probably the most common. They deal with money and so forth. But what we want to do is see, why are they terminating? Why do they stop? And if they do stop, maybe we can name them more easily. Okay, so good to know. Grade 4, we're talking about decimal notation. And again, looking at kind of the language that we use decem or decem, which is 10. And with the deci is fractional pieces. So you'll see other things if you do go into sciences. They have a deciliter, a centiliter, a milliliter. Hold on, let's check that. So in sciences, they use these words as prefixes for Latin. And so centi comes like from the base of cent, which is a hundredth, milli, thousandth, deci, tenth. So these are kind of telling you that these are fractional pieces, fractions of a single liter. And then after that, you have a decaliter, a 10, hundreds, thousands. So you have a kiloliter for 1,000. So you get all these names and labels. So I think it's good to kind of understand where they come from. So decimals technically are always about tenths. We've expanded the use of that word to include everything that is written in what we call decimal form, which decimal form, though, if you think about it, is place value notation using a decimal. And it is under the assumption that we are using a base 10 system. You can have decimals in other number bases. We just tend not to use them. They are a little bit rare. All right, let's take a look at terminating decimals. So when you start thinking about a number, and they give a few examples here like dollars, right? Understanding what it means. So if you were really looking at this, this would kind of look like 9 dimes if you were getting change for it, and 5 pennies. So that would be 5 pieces that are hundredths, 9 pieces that are tenths. So we could write this in what's known as expanded place value notation, 2 groups of 10 and 1 group of 100. Now, if you really wanted to, you could actually write that with, how would I say, with exponents, probably the best way. So 1 times 10 squared plus 2 times 10 to the first plus 8 times 10 to the 0. Remember, to the 0 power would be groups of 1 plus 9 times 10 to the minus 1 plus 5 times 10 to the minus 2. So that's the way that we could write this in expanded place value notation. And if you wanted to, you can kind of look down here. They have taken those 10 to the minus 1 and 10 to the minus 2 and written them this way. Now, what's interesting is that the way we say these numbers doesn't always match the fully expanded form. And let's take a look. So again, ones, hundreds, tens, ones. We tend to use the word and when we are representing the change from whole numbers to fractional pieces or to decimals. So like 3 1/4, like we would have said back in chapter 6, 3 1/4. That's 3 plus 1/4. That and is representing the fact that we are adding on and combining this with some numbers that are not whole numbers. Okay, so there's our and. Now, if you take a look at how we actually would read this number, though, we would read it as 128. That part seems fine. Again, that's the whole number portion. We use the word and to represent the decimal point. And then what we do is we take all of the decimal numbers and we see what's the furthest place value. And then what we do is instead of treating them as a 9 over 10 plus 5 over 100, we group it all because this is really the same thing as 95 over 100. Now you could see that if you wanted to, you could write this as 9 over 10 plus 5 over 100, get a common denominator. So we're going to FLOF. And when we FLOF, we get 90 over 100 plus 5 over 100. Same denominator gives you 95 over 100. So it's a really convenient piece, though, to understand, look, if I have 2 decimal places, when I write my number, I end up with 2 zeros because each one is kind of representing a group of 10 that I'm multiplying. Okay, so the way we word that last little piece is we, instead of saying 9 tenths and 5 hundredths, we would just combine it all together and say 95 hundredths. And that's what you'll see when we write it out. Now, please make sure at the end, don't say hundreds. Make sure you include the THS at the end. The THS is the part that is indicating to everyone that you are talking about fractional pieces. Okay. All right, let's take a look. All right, all good there. So I'm going to delete these and continue on. So you'll have a few of these to try kind of in the textbook. So if you had this, what a wonderful what a wonderful number to come in next. But again, if it was a pretty large number like this, that's okay. 12.61843. If we gave it its actual name, we would say 12, because that's the whole number part. and that's the decimal part. And then we take all of this and we write that in kind of the fractional part. So take a look though, it's 5 digits, which means I will have 5 zeros and 61843. Okay, so that's if you look at it, 61,843 hundred thousandths because it's in the denominator. Okay. So I would write out 61,000 843 hundred thousandths, THS at the end. All right. So there we are. So that's how you could write it out and say it. This is how we typically say it. Probably now, some of you are probably used to saying 0.618. But it does, I feel like that means you're not really seeing the actual place value of the numbers, right? Like what is the 8 in here? What place value is that in? And you can't say 0.008. That's not a place value. What place value is it taking up? Okay. So there we go. Keep that in mind as you go through these numbers. Okay, representing terminal or terminating decimal places. You could do them with the poker chips again. All you would do is say, here's my whole number, and then it takes whatever your base is, like that number to get up to a whole number. So that gives you, in a sense, tenths, even though you don't have to like break the chip up anymore. You could use them with the base 10 blocks, where you just change what your ones value is. Now your ones value is a rod, and then the little tiny cubes would be tenths. So if you're making 5 and 4 tenths, which is what we have here, 5.4, I'd have 5 ones and I'd have 4 tenths. So that's how you can physically represent it for students who are kind of learning these pieces. Again, the big piece to remember is that you should be thinking about your what do I want to say? You want to think of your what is your whole? What is your one unit? You got to make sure it's clear to anybody who's doing these. Okay. Yeah, so they could, depending on what they were thinking of as their whole. Here they're thinking of the whole block as the whole. That way they can get tenths, hundreds, and thousands. Again, that's totally fine. You could use these on what are known as decimal grids. Decimal grids are something that depends on which school you're in and how much they have for a budget, but they might be photocopying these so students can kind of shade them in and see about how big it is, so that they understand that 0.4, which is 4 tenths, is less than half. They can kind of begin to see that on the shape because of the shading that's there. All right, so now big pieces as we convert fractions to decimals, decimals to fractions. This shouldn't be too bad, the converting of a decimal into a fraction. Well, this is actually converting decimals to fractions to start, even though the title says converting fractions to decimals. Because I think when you see how easy it is with a decimal number to turn it into fractions, you realize that you can say it. If you say the place value notation, you actually have the fractional piece. 5 and 3 tenths. Boom, there's 5 and 3 tenths. I could write it as a mixed number. I could write it as improper. Both of those are just fine. If you read this one, this says 2 hundredths because I'm 2 place values in. So I would write that as 2 over 100. There's my common fraction number. Okay. 2 and 103 over 1, 2, 3, 4 zeros, which would be 10,000. So 103 10,000ths, and that would be the way I could write that fraction. So again, not too bad. It's actually fairly quick. If you do have the opposite value, just make sure that you do the opposite of that whole number. It's almost like you want to, when I do these, I would think of this as 3 and 6 tenths. Find that fraction, which would be 3 and 6 tenths. And then when I'm all the way done, then bring that symbol back in. Okay, and that's how you can get there pretty quickly. Now, when you see the title of this, again, the title of this section is terminating decimals. Like, what the heck do they mean? Terminating decimals are decimals that stop. So you see how it goes 0, 1, 0, 3, and then it stops. We're going to see other decimals that keep going forever. Okay, they are called repeating decimals. And they may also be called irrational numbers because they go on forever and they never repeat. So we have three categories of decimal numbers. We have terminating, repeating, and then those that are non-terminating and not repeating. Let's see here. So you've got a couple now. It says convert the fractions into decimals. There are a couple ways to go. If you have groups of 0, right? Hundreds, thousands, 10,000s, whatever is in the denominator, you can look at this and say, if I had 4 zeros, then I would have 4 place values. So that's one way to do it. And then fill in the 205 starting from the right. And you may need to bring in an additional 0 like I've done here. And then typically, I think it's best to write a 0 in front as well. And the reason for that is if you get used to not writing these other zeros down, you're missing place value. But then as well, if you write it in such a way that your decimal point isn't clear, it could look like a much different number. Not that everyone's going into the nursing field, but in the nursing field, they are very particular about how you write your numbers. Because if you accidentally, like if there was a line and you were writing down 0.2 liters of something, and you put your decimal point and it looks like this, 0.2 liters, that point might get lost in the line, right? Because it's going to be very hard to read. So they would typically write a 0 in front. And that way, if you saw 0.2, somebody go, what the heck does that mean? And they would go and clarify and confirm that it actually is 0.2 and not 2 liters. Okay. All right. So if there are zeros, again, here, 2 zeros. So just put a decimal point and then think of 2 decimal places. Start from the right and write like this. And then again, I usually put that 0 in front just to indicate that this is a number that is less than 1. Okay, those are pretty quick then, right? So if you have denominators that are perfect powers of the base, 10 to the n, right, we'll have, and this I should say is 1 over 10 to the n, we'll have n decimal places. This right here is 1 over 10 to the first power. You can see that in the denominator here. So that has 1 decimal place. This is 1 over 10 squared, so it has 2 decimal places. This is 10 to the fourth, so it has 4 decimal places. So again, that's kind of the idea that I hope helps you make that connection. Okay. So if you do encounter something that is not looking like this, you could, let's just say we had 2/5, right? You could say, okay, 2/5, 2/5. Oh, wait, there's no tens there. But that's where all of our learning from chapter 6 comes back into play. And we could say, oh, but if I fluff this, I get a new fraction that is equal to what I started with. And now it does have a perfect power of 10, which means there's 1 decimal place. And I'll put the 0 in front. And that's why 2 over 5 turns out to be 0.4. Okay. How else could you get there? You could do long division. You could say, I want to put 5 into the number 2. And we know 5 goes into 2 0 times. When we multiply, we get 0. When we subtract, we're left with 2. And now we could say, but wait a minute, let's take fractions and parts of that number instead of just saying remainder of 2. Let's put the decimal point in which case we are now talking about tenths. How many tenths of 5 would we need? Well, think about it. If we come to the next place value and we continue with our same process, 2, the number 2, is the same as 20 tenths, right? Okay, so 20 tenths, when we say divide by 5, you have 20. 5 goes into 24 times. 4 times 5 is 20. But really, we have 4 tenths multiplied by 5, which gives us 20 tenths and no remainder. And so this is a second way that you can see how to convert a fraction into a decimal. So we have division and we have building up. You have those two options. Both are perfectly acceptable. Sometimes one's easier than the other, if you want to be perfectly honest. Okay, school book page. This one looks a little bit blurry for me. Hopefully your scan turned out a little bit better than that. But writing decimals that are equivalent to the given decimal. And this is really saying that you kind of the understanding from a student's perspective, this is again a grade 4 textbook, that if you had something like 9.1, that you could write it as 9.10. So this would be like in money, we would say $9.10. We wouldn't say $9.01. Okay. Because again, it would be 1/10. Most of our money comes in the form of hundreds. Okay. And if we were talking in a science classroom, maybe we have a very, very, very powerful scale. We might be able to say that we rounded correctly to 3 decimal places. That's how good our scale is. So all of these represent the same decimal. They're just different ways of writing it. Okay. All right, let's move on. All right. So what we're looking at here is to multiply a decimal by 10 to the n, move the decimal place. To divide by 10 to the n, you move the decimal place the other direction. So this process is, there's nothing wrong with this. So let's make sure we understand what it's saying. If I have something like this, this is the same as 56 over 10 squared. Then take a look at the exponent. The exponent is 2. So what we do is we don't have a decimal place listed in the number up top, so we put a decimal place in. And when you divide by 10 squared, what you do is you take that decimal place and you move it 2 places to the left. And it says adjoining zeros if necessary. So when I rewrite this, as I move it 2 places to the left, I would have 0.56. That's what this little piece here is saying. Okay. Now, you start with easy ones, right? Notice they've given you 3 over 5. How could I do this? You could use FLOF. Build it up. Get 6 over 10. A 6 over 10, we know, is 0.6. What that means then is I have to be able to make this into a power of 10. I have to be able to say I end up with 10 to some power at the end of the day. So if I have 3 over 5, that's going to work out perfect. If I have 5 over 7, can I rewrite this as 10 to some power if I FLOF it just right? And what that would mean is that, what? 7 would have to divide 10 to the n. This goes back to chapter 4. And this is that fundamental law of arithmetic. 10, as we know, 10 is 2 times 5. What does that mean? 7 is a prime number. 7 does not divide 2, and it does not divide 5. There's no way it's going to divide into 10 to the n. It's impossible. So that also means we are very limited in our terminating decimals. Our terminating decimals have to be powers of 2 and 5 only. So that's why this one worked out really nicely. It was 5 to the first power. Okay. So if you prime factor and you can get it down into 5s and 2s only, then it will terminate. That decimal will terminate. So if you take a look here, they've given you a lot of different things, which they do look confusing, but they're actually, I don't know, I think they're kind of fun. So here, what is this saying? Well, this one's going to need a calculator probably because I don't want to do this by hand. However, if you look and you just say I need to build it up to get that power of 10. You need to make pairs. 2s and 5s pair up to make 10s. So if I have 6 2s, I need 6 5s. Multiply them, and you will get 10 to the 6th power. Not a coincidence. And then move that decimal 6 places, and there you are. You could also draw in the 6 place values like I did before, and just write your number in starting from the right. Perfect. Some of them are quicker though, like this one. If you look, I have 2 to the 3rd power and 5 to the 4th power. When I look at that, I've already made a bunch of pairs, like almost like 0 pairs, but it's a 2 and a 5 pair. A 2 and a 5 match up to make a group of 10. What I'm missing though is I'm missing one additional 2. So if I multiply by 2 on top and bottom using FLOF, then I get 2 over 2 to the 4th times 5 to the 4th. And that, my friends, is 10 to the 4th. And 10 to the 4th has 1, 2, 3, 4 decimal places. start from the right, and adjoin zeros as needed. There it is. Okay. If you cannot see a number quickly, break down into prime factorization. The number 250, right? That's what? 10 times 25, which is 2 times 5, and 5 times 5. Got it. So this is 2 times 5 cubed. So think about those pairs. I've got enough 5s right now, but I need some more 2s. I better multiply by 2 squared to build that up, so I have 3 of them. And that is indeed what we do. We multiply by 2 squared, top and bottom, so that I get 3 pairs of the 10 pieces, and I end up with 28. Again, 3 decimals showing works out perfect. Now, here's the issue. Most of you are probably saying, well, why don't I just grab my calculator? Your calculator is a great tool. The issue is that for some of these, your calculator will not display infinitely. It stops. Maybe it's a 7-digit display. Maybe it's 9. But it will eventually have to stop because the numbers will continue on much longer. We need to have techniques that will show us how do we figure out what that decimal number is, necessarily without a calculator. Okay, so we can look and see a number is not 0. Your calculator may say that it is 0. It may also put a number in scientific notation, and we'll see that in this chapter as well. Okay, well, let's continue on and see some other cool ways to do it. So calculators do convert. Some of you may have, depending on your cell phone, you might just use your cell phone to check it. But if you use an actual calculator, when you do the division, it should put it in decimal form. Sometimes it'll have a button that says something like F to D, fraction to decimal, and it'll go back and forth, which is kind of nice at times to see the fraction form and the decimal form. So here we go. We're going to define terminating decimals. These are numbers that can be written with a finite, not infinite, doesn't go on forever, a finite number of places to the right of the decimal point. So if we attempt 2/11ths as a terminating decimal using the method we developed, we try to find a number that we multiply by 11 to get a power of 10. What could we multiply by? Well, back in chapter 4, fundamental theorem of arithmetic says we cannot write 11 as a power of 10, even if it's 11 times b, because 11 does not divide 10. So a rational number in simplest form can be written as a terminating decimal if and only if the prime factorization of the denominator contains no primes other than 2 or 5. Now let's take a look at some of these. They're not trying to be tricky. They're trying to make sure you think about what this definition means. First off, what do we need? A rational number. We're dealing with fraction-looking objects. Notice next, simplest form. Hey, that was just on our test. What does it mean to be in simplest form? Okay. And then the prime factorization of the denominator contains no primes other than 2 or 5. These are okay. So when you start looking at some of these, like this one, 21 over 28. So here's what happens sometimes with students. They'll read part of the definition, 28, and they'll say, oh, that's 7 times 4, which is 7 times 2 squared. And they'll be like, uh-oh, it says it can't contain any primes other than 2 or 5. And that is 100% true if you read the entire definition. Notice it says a rational number in simplest form. In simplest form, if you look in the numerator here, I get 7 times 3. The 7s eliminate because of the multiplication and the fundamental law of fractions, which means I end up with 3 over 2 squared, and boom, totally, this can be a terminating decimal. Okay, and I can see I have 2 2s. I pair that up with 2 5s, which is 25. And 25 times 3 becomes 75. This on the bottom becomes 10 squared. That's 2 decimal places. And I get 0.75. Okay, totally terminating decimal. So make sure, first off, do you have rational numbers? Second off, is it in simplest form? Now look at the prime factorization to see whether it works or doesn't work. Because you will find some, when you prime factor them, they do not simplify. Even though you may have students who will come along and say, oh, but the 3 goes with the 3 right here. No, the 3 in the top part is a digit. The 3 in the bottom is a factor, and the fundamental law of fraction says they have to be factors to do this. All right, let's take a look at what comes next. Clear those drawings out of here. And here's using decimal grids and also ordering terminating decimals. So just understand, a lot of times students will look at the decimal part, and because you're saying numbers, they will see things differently. I'm not gonna lie. So example, if I said 0.9 and 0.44, right? If you look at this first one, we would say this is 9/10, right? The bottom one is 44/100. Awesome. What a lot of students will do when they see these is they'll look and they'll say 44. 44 is bigger than 9. So 0.44 is greater than 0.9. Okay. So you might remember when we were comparing fractions, though, if we were comparing like 2/3 and let's say 5/6, right? We couldn't just look and say, oh, the 5 is bigger over here. A bigger numerator means the fraction's bigger. No. We couldn't look over here and say, oh, the 6 in the bottom, a smaller fraction comes when you have a larger denominator. No. What we would need to do to compare them is, most of the time, create a common denominator. So we would FLOF, and this would be 4/6 and 5/6. And now that they are the same denominator, you could compare them and see which one is bigger. And that is how we could do it. The same concept holds true when you come back to what the student was struggling with. We are not comparing like objects. One is tenths and one is hundredths. Okay. So we would need to say, I need to convert this. So the 0.9, the 9/10 would be the same as 90/100. Now you don't have 9, you have 44/100 compared with 90/100, and you can immediately see, got it. I can tell why 90/100 is bigger than 44/100. So there's sad face, here's the happy face. Okay. So again, you can kind of see we can order them because they are terminating. We can always find a common denominator. It'll always be one of those powers of 10, and we can line them up correctly. Okay. So again, here, 0.9 to 0.36. 0.9, definitely bigger than 0.3, right? So the fact is right there in the tenths place, the larger one will immediately be larger. So that, again, it's a kind of a quick way to think about it. Okay. There's some practice, figuring out which ones are larger, which ones are smaller, getting some grade 4 practice. And let's see here. Oh, we're getting into the assessment. So yeah, here we go. Two fractions can be compared by looking only at the numerators. Once you have the same denominator, you only have to look at the numerators. But you also have, if you remember that Kool-Aid property, I mean, you could use it again here, but you may not need to, because the Kool-Aid property was to try to find fractions between fractions, right? So here comes something that is kind of helpful here. So if I had 2/10 and 3/10, a student might look and say, ah, there's no fractions between them, or that there are no decimals, whoops, 0.2, 0.3, no decimals between these. Okay. So remember your fundamental law of fractions. This allows you to FLOF. And if you FLOF with tens, you'll end up with equivalent fractions, right? And the decimal places will then look like 0.20, 0.30, because two decimal places means two digits. Okay. Now it might be much easier to see, are there additional decimal values or fraction values between these two numbers? The answer 100%, right? Because now you have 21 over 100, 22 over 100, dot, 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 dot. And boom, we're back to it. All right. So if you need decimals between decimals, as long as the decimals are different, you can always just build up that denominator a little bit and you can find additional values. Okay. All right. That's it for this first section, 7.1. Hope it worked out for you. Let me know if you have questions. All right, off you go.